understand the things in more intuitive way, like how the things are behaving. So what are topics has been covered, I have tried to cover in more intuitive way. So this is a table of content. So more or less whatever you have covered in this is recent 8 hours or something has been covered in this session. And we have like I have put the things in more intuitive way. So we'll start one by one. So whatever so far we have seen in sampler distribution, all the testings and all that has been done for the continuous variable. When there is a population, for suppose you have a population, okay, you have population for which the mean is 25. Like consider this example of bolts, right, in a factory or something where the bolts are being manufactured and there is a population. Then you take a sample out of it, right, of this complete population, take a sample out of it. The frequency of those bolts might be like this, the distribution of those bolts, and you get this thing, a sample of this bolts. So the objective of generally this thing is, based on this sample, can you say the process is working fine, right? Because your specification of the bolt size for suppose 51 plus minus some deviation. So based on this sample, can you say something about the population? That is, so initial five, and I'll talk about the basic, then we'll go much more advanced way. So can we, based on this sample, can we talk about this population? That is the general objective why we do the sampling, right? So generally this decision will depend on the original population standard deviation sigma. So for suppose this standard deviation is from 10 to 30, 10 to 90, right? So the sample which will extract, which may fall anywhere, right? So that decision will depend on the sigma, number of samples taken. If you're taking very less number of samples, for suppose 5 samples you have taken, you can get from here also, you can get from here also. So that's why these two numbers are very important. Then this population and sample mean for reference when you're comparing the things. So this is the objective generally we have for the sample distribution, like why we are taking out the sample and why we want to say something about the population based on the sample. So if you see the central limit theorem, though, so then generally there is a complete population, right? So you take out a sample, then you take a mean over here. Okay, so that means come over here, right, of this population. Then again you take another sample for different, it may be some different sizes of the nut bolts. Then you again put its mean, the sample mean over here, again that mean come over here. You take some other sample of different, something different will come out, again you keep the mean over here, right, the mean of this samples. Then again you take some different sample from the same population, the mean sum will come over here. So this distribution of the means is called sampling distribution of sample means. So we have the sample means, and you put this distribution, this is called sample mean of sensitive distribution. Consider this now, keep on taking the sample 10, 10, 10, 20 samples and keep on putting this. This follows a normal distribution, right? I'll show you intuitively in the Excel sheet so that you can understand what actually happens. So for suppose I'll consider example of dice throw, right? So this I have used random function between 1 to 6. Right, so if I put a histogram of this, so generally you know that the histogram of dice, so number of bins will be 6 over here, keep it understanding. So this is uniform, right? This is, if you are taking the samples, like if you're throwing a dice and you're throwing the dice around 1,000 times, and also all the samples will be uniformly distributed. Now consider this, I have taken one sample, then two samples, then I've taken the mean of this. So mean of this two, the numbers, two numbers, right? If I put this one, oh sorry, if I put the histogram of this one, so this is normally distributed slightly, right? Now if I take 6 samples like this, 1, 2, 3, 4, like so, from this same samples I've taken, this is a random function which I've used. Out of this sample I've taken one sample and two samples and all, maybe up to 10 samples I've taken out of it. Now if I put this one, we follows a more normal distribution. Now what happens, why it's coming closer and closer, I'll tell you one next example also, right? So if you see the width is getting decreased, center is getting more increase and width, and it's following a normal distribution. This is called central limit theorem, whatever this distribution is. But the mean of the samples, this sample has been taken from this original mean, or this original population. If you see the function which I've used in Excel right now, so I'm taking one sample out of this total counts, right? Not, let me give you more intuitive understanding on this one based on this example. So what I have done in this case, I have put probability, random probability between 0 to 1, right? Different probability. Correspondingly, I am putting a normal inverse function. So I'm getting a normal distribution. So if I plot this thing, so 1,000 numbers are there, right? 1,000 is my population right now. If I take the histogram of this one, right? This is a normal distributed curve which I generated, right? Now what I'm trying to do is over here. Now how I'm doing it, the normal distribution when I'm doing it, I'm taking a mean of 100, right? And I'm taking the standard deviation of 10 over here. Now if you see the standard deviation, if I calculate by the function of this complete population, I'm getting approximately 9.26 and mean is 100 approximately. Now from the same 1,000 distribution, I've taken one sample like this. This is random between this complete sample. I've taken one sample, then two sample and three sample, four sample, five sample, six sample, right? So this is basically my sample. So I've taken six samples out of this, right? Now, if I take the mean of this, all these six samples, right? This follows different distribution, which should be normal, right? Normal in size. One more thing, I'll come back again. Come back again over here when I want to show the t-test and all those things. What is the sample, standard deviation, and all those things. But if you see now, this mean of this is 100, but the standard deviation is 3.70. Can you see this thing? So this standard deviation based on this population is 9.26, whatever I kept over there. But for this population, it is 3.70. So consider a thing why this narrowing down is happening of the standard deviation, because at any point of time, if I'm taking for suppose these two samples, if I take the mean of this one, it will come lesser than 100 only. So the outermost point which are there, they will try to come converge to the centers. Because if I'm taking a mean of these 2 points, it will converge towards the 110, right? It will not be the outliers. So what happens when you take the mean of the multiple samples, so the outermost value just try to converge to the centermost. That's why when you know this formula which is there, standard deviation divided by square root of n, right? I'll come again on that particular point. So as the number of sample increases, your standard deviation keeps on coming towards the center, because the the outside value which are there in the range, they keep on converging toward the center. Because if I take the mean of 121 and 72, right, it will be center of this will be not come as a mean, right? So this is a thing which comes into play. I hope I'm clear on this one. I,
Yes, Vishal.
yeah, again come on that Excel sheet when I have to talk about the sample. So generally we use there are three things, right? So hypothesis में one sample, two samples and all. So one sample में what we do, there is a population, right? We take a sample out of it, and this is a sample, right? Out of what we discussed. So based on this, with respect to this, can we say something based on this sample? We have to say something about this. So this is the one sample, and this, you know about this t test and z test, one sample and all. So null hypothesis says that both are same, and alternate hypothesis both are different, right? So all the generally statistical test, like always the null hypothesis says that the two things are same. Similarly, for the paired test, relative test. So relative, I mentioned relative because when you have to use a t-test, you'll use a REL word over here. So consider relative over here. So I'll tell you why. For suppose there is a original population, original process in your machine which is there in your factory. You made some process change. Now you want to see whether my process is changing. Like my sample is, for suppose earlier my sample mean was 51. I wanted to improve and make it 50, my all the nut bolt sizes, the mean. So you want to see the impact over here. So what you do, you take a sample of this one, the new process which you made it, then you take a sample of the old one, right? Then you compare these two things. So you, for suppose the medicine you given to some people, right? uh, some medicine you given to some people, you want to see the impact of that. This is like this. So the old sample and new sample, then you want to compare based on this with respect to the effect of this, the process change. So this is called two-pair relative testing. Again, when you have independent samples, you have two machines, right? One is machine A, one is machine B. Then you want to compare it, how they are behaving. Then you take a sample of machine A, then you take a sample of machine B. Then you compare these two things. These are called independent samples or unpaired samples. So, but rather remember by independent rather than pair and unpaired. It will be easy for you to remember by this, based on this, because the same function you're going to use over here, independent and relative, and it will be easy also. These are independent things, right? We are comparing two independent things. So now, what is Z distribution versus T distribution? So when a sample of n observation is taken from a normal distributed population having mean mu and a standard deviation sigma, the sample mean x bar, which I showed, the 5-6 sample I've taken, the sample standard deviation s differs from mu and sigma because of randomness of samples. Now again, I'll go to the Excel sheet. I'll show you what is this. So what it's saying is this was the population standard deviation, but this 6 sample which I've taken, if you see the standard deviation of 6 sample, this is 16 in one sample, right? Again, 5 sample I have taken. This is coming 7.6. So it's not coming 10, right? Sometime 1.9, 5.6, 4.7, and so on and so forth. So what's trying to say is the standard deviation of the sample will vary based on the sample, how much number of samples you have taken, right? So the same thing is being told over here because of the randomness of the sample. So this S, which is a sample standard deviation, and the sample mean, they will vary. Now the T distribution is also known as, student people know that it's a probability of distribution when that is similar to normal distribution and bell shape but heavier tails. Heavier tails means so they have more chances of outliers. They're more affected by the extreme values because the normal distribution tends to be flatter over here, but T distribution actually is much more thicker at the ends. So the tail heaviness is determined by the parameter of T distribution called degree of freedom. Degree of freedom is nothing but your I'll come on that, but degree of freedom is nothing but the sample size minus one. So if you see one over here like something, the distribution for suppose nu equals to 1 is this yellow one with very heavy tails. As on you keep on increasing the sample size, this distribution becomes more normal, and this thickness of the tails keeps on reducing it, right? So this is called effect of numbers sample size on the T distribution. So this is similar to the cumulative distribution function, CDF function. When the sample size, like degree of freedom, is less, so it becomes more heavy. So if you see at very high value also, very less value also, you don't get a zero. It's some value over here, right? So just for knowledge, the probability.
Vishal,
Yeah.
one question here.
Yeah.
That black line one, right? Okay, minus v equal to plus or minus infinity. But
Correct.
you should not touch that line, right?
It will touch that line.
It seems like it is touching the line.
It will touch
It is
that line.
touch. Okay, but as per the rule, right, it should not touch that line, isn't it?
No. See, this is infinity, right? Again, it's infinity. If you see the black line, so infinity means number of sample size is infinite. As per the rule, the number of sample size is infinite. Now I'll tell you why it's happening. So imagine a case when I'm taking all the samples altogether, right? I have taken 5 samples. If I consider total population over here in the horizontal way, so all the population will come over here, same way. So the standard distribution of that one will be equal to this one only, no? And the mean also will become the same. So basically, as it is the complete population itself, I'm taking over there. You're getting my point? N means what? N means infinite, means I'm taking whatever population. For suppose there are 1,000 cases, 1,000 numbers are there over here. All the 1,000 if I'm taking, the sample itself becomes the distribution itself, no?
Yeah, but the actual population itself, right? It will not touch the line, isn't it?
No, it will
That's my
take the line. No, see,
understanding.
right now I've taken 1,000 sample. I have put it the normal distribution over here. If I take 10,000 samples over here, so it will become normal distribution, no? Because all
Yeah,
about
no,
how much you're normalizing and the number of bins you are keeping over there. if I'll show in the Python also. So let me show in the Python itself.
Okay.
Okay, so now take this example. I have taken line space of 1,000, right? I'm again plotting a PDF function, right, with some LOC and some scale. If I'm plotting this, I'm getting exact normal distribution function, no? Because I'm taking 1,000 samples only over here, right? It's exactly normal distribution, right? If I take now as a sample, if I take all the population itself as a sample, my sample will be similar to the population itself, no?
No, actually, what I meant was that line, right? Below zero, there is a line, the horizontal line, isn't it?
Just
So
one second.
that line and the normal distribution line, okay, will not fit into that same line, isn't it?
Yeah, Vishal, what he's saying that you know the line right and left hand side line, right? You should not touch x-axis. That's what he's saying.
Yes. Yeah. That's what I meant. Yeah.
You're
You
talking
are
about
right.
this one?
Yes,
Yeah.
correct.
Yeah.
Should not touch.
No, they will test. Reason is the normal distribution. If you see, no. So what happens is the probability is very small. That's why when you calculate, for suppose a small p-value, you get a very less probability, right? As a cumulative probability. This is CDF function, which you use to calculate the p-value also, right? Now imagine this a 0.05. Can you imagine where it will be? This is 0.2, this is 0.1, 0.05. Can you imagine where it will be? Very less, right? So that's why when you are saying it at this particular very less near to the zero, the probability of getting something less than or higher than that is very less. So 0.05, can
Uh,
you imagine like
Yeah,
that?
ideally it's greater than zero.
No, that's what I'm saying. It depends.
Mm.
It depends at which point you are saying. If you are near, see, this is a standard normal distribution. Please see this. This is standard normal distribution, right? This is with a mean of 0 and standard deviation of 1. This is standard normal distribution. If you're plotting any something else, this frequency, this will be frequency. This will not be standardized. You're getting my point?
Can you
So
please
Vishal,
can you
Praveen
please
here. In the normal distribution, right, the tails will run in parallel. It will not touch the x-axis. That is the whole basic funda that was told, correct?
So even if you see this,
Actually, what he means is like it's asymptotic, right? What you mean?
Yeah.
It will be running to
See, if you
parallel
see,
to x-axis,
yeah, it
but
will
it will
parallel
never
to
touch.
x-axis. Correct.
so talking about this graph only, or you're talking about degree of freedom? So earlier I was thinking of talking about degree number sample size, because this degree of freedom is depending on the sample size. Are you talking about this probability which is touching to x-axis like 0? Do you have a problem like that is this t distribution is meeting the normal distribution, or you are having problem that this value is coming to 0? There are two things. One is when the t distribution exactly approaches the normal distribution.
no, Vishal, we need to see what is the least probability, whether it should be higher than zero.
No, that is okay. That is this is the y-axis. See, that is okay. But you have to see that when the number of sample size is reaching infinite, the distribution itself is touching the normal distribution, whatever distribution, like whatever it is, but it is touching the normal distribution. See, the value I'm not putting, no, because if you magnify, right, it's not magnified scale. If you magnify this, it will be my 0.00001. But in the scale, you cannot see, right, that thing. This is just an image, right? If you keep on magnifying it, then you may be able to see it.
Yeah.
Correct?
Yeah. Please. Yeah.
So objective was
Thanks.
here. The objective was here, like if the sample size is going to infinite, the distribution will exactly match the normal distribution. So this if I keep on magnifying, right, it will be 0.00000. What you are saying, I understood your point. You are saying it will not be 0, it will be 0.0000 something. But you cannot demonstrate right over here that thing based on the image
So,
that is
Vishal,
Yeah.
Vishal Nikhil here. So, what I think you're trying to say is that if you keep on increasing the sample size, that eventually become a population.
Correct.
And what population
Correct.
is? it tends to that everything tends towards the mean and median.
Correct. Correct. Uh, so again, so in the hypothesis testing, there are two things, right? People know. I'll not go in more detail. Like the population, when there's known, you do the Z test. When the population is not known, use a T test. So again, in the Z test, this is a sample mean. Maybe I'll use a pointer. This is a sample mean. This is the population mean, and this is sample population standard distribution. In these tests, use a sample standard distribution, and this is called standard error. Now, if you see, when you talk about this thing is the sampling distribution of sample means, which is following a standard deviation of sigma by root n. I showed you over there also in the Excel sheet. If you see this, this is my sampling distribution of sample means, right? This is the mean of this sample. This is the mean of this sample, right? So this is my sampling distribution of sample means, and it follows the standard distribution. If you see, is coming 3.7. If you calculate by formula, sigma by root n, sigma is 9.26 by root n, root of this 6, right? You get the same value, 3.78. So sigma by root n is similar over here, right? So when you put the distribution of the means, then you get the sigma by root n, correct? So if you know now, in case this sample size becomes very high, so what will happen if I add 10 more maybe samples over here? So this will exactly match with this thing, right? Now second thing is the standard sample standard distribution, right? Or the standard error. So one more thing, if you see over here, is the standard deviation of the samples. They are distributed like this, sometime 12 16.6, 7.6, 12.2, 1.9 also, right? They're very different. But in the T distribution, you don't know the sigma, right? So you cannot calculate the sigma by root n. So in that case, what you have to do is, the sample's standard deviation is there, then the same sample standard deviation, you use it and you divide by the square root of n. So this is the value you get it. So if you see, sometimes you're getting similar to this value, 3.7, sometimes you're getting high value, sometimes low value, but approximately better than these values. And if the number of sample increases, let me increase the number of samples over here. Let's do it. Just 1 second. Let me add some more samples over here. Can you see this becomes better and better? This becomes better and better over here. And this mean distribution, if you see that, this comes near to the 10. Earlier it was 1.68 and all those things. So as my number of sample is increasing, my sigma by root n, or like standard S by root n, is also becoming more equal to this one. You getting this? So this is the significance of standard error which you talk about. So you calculate the standard deviation of the sample, then you divide the number of by the square root of samples. That's how you do it. So this is called standard deviation of sample. Am I clear on this point?
Yeah.
Yeah.
So I already showed, right? Sample standard deviation is the deviation of the individual data points on the sample means. When doing the differential statistic, we were able to see something about the population. I'll maybe leave it. We could get such.
Hello, Vishal.
Yeah, tell me.
Sorry. Hello.
Yeah, tell me.
Yeah. Can you go back to the previous slide once?
This one?
Yeah. Yeah. So if you see in ZStat and TStat, now the denominator part. So here we are computing on the population mean, population standard deviation, and here we are computing based on the sample stage standard deviation.
Correct.
So what is the reason for that?
because you don't know, no, here you don't know the population standard deviation, no? And
Oh,
you're
okay.
approximating it. You are approximating by taking the sample standard deviation itself. So if you see here, if you see again, so you don't know like what would be my sigma value, but based on this sample, for suppose 13 sample you have it, based on this 13 samples, you are calculating this. So if you see this standard deviation, which is coming very near to the 10 value, right? Not exactly, but
Mm.
sometimes higher, sometimes lesser, and all those things. So when you use over here, you use sigma by root n, right? Sigma is 10 over there, but here you approximate by taking the same standard deviation of the sample itself, which is not 10, but very near to this value. I showed you, right? If I keep on increasing the number of sample, this value will keep on becoming near to 10. That is the beauty. And then on
Okay.
this standard deviation, you divide by square root of n, and then you use it. So you don't have the standard deviation of the population, but you have the standard deviation of the samples itself.
Okay. Okay.
Clear?
Yeah. And one more thing, means that time Sayan had mentioned that it's not, it's actually irrelevant with respect to the sample size as well. When we try to like, when we are trying to compare between Z test and T test,
Mm-hmm.
so when to go with what? So it also, I had read in one book that we also compute based on the sample size. If its sample size is more than 30, we go with Z test,
Theoretically, it's
or
mentioned
else.
everywhere. Yes, theoretically. So if I, that's what I'm saying. If I keep on increasing the sample size, let me show you also. Why not? Let's do it. Let's do it. Let's make it. Let's increase it. Anyhow, I made a code like that. It will automatically adjust. Right. This is 26 samples. Square root of count actually. 1 second. Why not? Let's do it. Let's see. So my now I've taken 27 sample approximately. Can you see the standard deviation? Can you see this? This value is is that more or less matching with this value now,
Yeah,
right? This
nearing
sigma by
to.
root and sigma is population mean over here,
Hmm.
right? This is population mean and square
Yeah.
root of n 27 samples is considering, and this is coming 2. And the same thing when you're doing this based on sample standard deviation, if you divide it by square root of n, you're getting more or less same value. If I just reduce the number of samples, if I just make it only 6 sample or 5 samples, see the difference. This is 4.23, but this is 3.6, 2.9 and all. So as the number of sample increases, your sigma by root and your S by root and both becomes more or less same. That is why the 30 number is coming into play.
Oh, okay. Okay.
Okay, we made 27, right? Again, see it.
Yeah, yeah.
See this. We 27. In that case, more or less, these values are similar. But
Mm,
if
yes.
we make it very small number of samples, this and this becomes very different actually, right? So as higher number of samples are there, both will give you the same value. This and this will give you the same value
Okay.
because this denominator becomes the same.
Yes.
Correct.
Okay. Thanks, Vishal.
This was quite interesting thing. I also tried to do in Excel. Actually, want to do something visualization. I want to see how it's behaving. That's why I did in Excel, so I can see what is happening. Something interesting to people like this thing. How to see this? How to visualize? Intuitively, we got it. Why I named this as an intuitive session?
Yeah, sure.
Yeah, yeah, yeah. Yeah, it's interesting.
So now you can approximate the variability by using the standard error of the mean and the sample standard deviation divided by the square root of the sample size, right? So this is again degree of freedom I have showed, right? Sample size and the distribution will have n minus 1 degree of freedom. blah blah blah. It's not relevant. So these are the maths formulas and all. So if you see, there are majorly three things, right, which you have studied: one sample, two sample, and two sample independent, relative, independent. So this remains more or less same. Then you have, oh, sorry. Then you have for two samples. Again, this is x bar minus. Again, this formula, I'm not going to formulas and all. This is just I want to show you how the formula behaves and all. If you see in this case, if you just make n1 equal to n2, you'll get this formula. So if the number of sample size is same, you'll get this formula. Again, there are multiple things like equal, unequal sample size, similar variance, unequal sample sizes, and unequal variances. So there are multiple things. Again, it goes into like it divides in further parts, which I'm not telling you right now. Maybe you can go on Wikipedia. It's mentioned over. I'll give you the links, all the links which are there. Just want to show you how this like maths part of it. And this is a T table, how you see it. So based on the one tail and two tail, you see this values of p significant value or p value, corresponding degree of freedom, which is n minus one, right? Corresponding, you have to use the z value, which is coming up. This is how traditionally it used to be done, and what inside the Python it does. Now, if you use the Python syntax of these things is, you know that you have to use the norm.isf function or norm.pdf function of cdf function for the z test. For the similar one sample, you have to t-test dot one sample. For relative function, you have to t-test dot rel and t-test dot independent. One is something is there's a stats model. If you have to use a two sample test, if you have to perform it, you can use this or you can use the stats model dot weight stats. I'll show you in the exercise also. So this thing is there. Like if you have to use a two sample z test, it was not covered in the class, so you have to use this particular test over there. So this is how you import. You know these things. I don't know how to tell you like import. One thing I could not understand, what is this t-test power? I try to read it also because he imported this sign. If someone knows about this thing, it will be good if someone can tell right now. If someone knows about this, what is this t-test power? I try to read about it. I could not understand this in detail. What is this t-test power? Someone knows this thing? T-test power. What is this t-test power? Maybe please, if something read also something, please share on the group, WhatsApp group which is there, or maybe the Google Classroom. Because I read it, I can understand what is this t-test bar. Something confusing was written over there. Now very important thing is, what are the conditions for applying in z and test that test? It is very important thing, because you cannot just apply the z test and z test just like that. So first condition is the randomness of the samples. The sample should be random in nature. Second thing is the sampling distribution of x bar, the sample means, needs to be approximately normal. This is true if our population is normal or if our sample is reasonably large. But sometime in the large sample also you will find this is not good. Then independent. Individual observations need to be independent. Okay, our sample size should not be more than 10% of the percent of the population. For suppose you have 50 data points in your population itself, and you are taking 25 data points as a sample, then they are not independent. They will be dependent on each other, right? So this is a very important point also. Again, these three conditions should be met, then only we can use a t distribution. Okay, and one more point, important point over here is the original population need not to be normal. The sampling distribution of sample mean should be normal. Please understand this thing. It's very important. Your original population may not be normal, but when the sample size increases, the sampling distribution of sample mean may be normal. This is very important point. I'll come to. I'll show you the physical this one also, how this makes sense. Then something is called homogeneity of variance. Like variance among the group should be approximately equal, should not be very different. The variance or standard deviation which is there. One important thing, if you want to test the variation, right? Variation of homogeneity of variance, there is something called Levene's test. or bronze Forte test or Flinger clean test. You can use this test over there. It's just simple that you have to put the two samples in the leaving and you can test this. I'm just telling you the name, so you can also go through and test also, not a big issue. It's a small one line code for this testing the two samples are the variance of is homogeneous or not. Now, at the end you'll get the p-value, right? So my observation is my declaration is like if the two samples are similar, the p-value will be very high, right? Now, what to say the p-value probability of them being the same is very high. This is a p-value, right? So when the two distributions are same, even any test you are doing it, t test, z test, and everything, and you are doing it, if the p-values are similar, if the distribution are similar, then the p-value will be very high. If the distribution are different, the means are different, then the p will be very low. I'll come on that point when I'll come to, because last session people were getting confused with the Shapiro test also. Why the Shapiro test has a null hypothesis of when the p-value is very high, then it's matching. So because the Shapiro test compares the distribution with the normal distribution. So if the Shapiro in the Shapiro test, when it compares with the normal distribution, so it if the both the distribution are same, then the p-value will be very high, no? So that's why the null hypothesis was like that, both are same. I'll again come on this particular point. Just remember this thing, like just a easy thing to understand this. Now practice it. I'll again show you some things. Tell me if I'm going very fast in terms of talking or something. I'll make it slow. Am I okay? Because
Fine, Vishal.
and is it
Yeah, Vishal.
okay? Is it okay? Like what I'm telling, these things are very much obvious, or like or something you're getting out of it. I don't know.
Yeah,
Like,
it's fine.
Yeah,
Yeah,
it's
it's fine.
useful and kind
No,
of
this is helpful.
refreshing. Yeah.
oh, thank you.
Yeah.
So just recap on the normal distribution. You know this, you'd have done the exercise, right? So I'll not go in much more detail. When you do the z value, you calculate the z value out of it, and you use a storm normal distribution function. Then based on LOC function, you calculate the what his value is. The important thing is what I showed you, the normal distribution. Now let's not go in this one. I'll anyhow share this Python code with you. Now, one sample z test again. You know this is already covered in the class. So when we have a sample score of 100, IQ, the mean IQ is 115. They wanted to say that whether the mean is more than 100 for this particular people. So the X bar was 115, the sample mean was 100, standard deviation of the population was 15, and sample size was 100. So that statistics was calculated just like this. You have seen this. Based on that, they got the uh, value of Z statistics as 10, right? They calculated the Z statistic critical value was 1.64. So that means in the normal distribution function like this, the the critical value was 1.64 somewhere, and you're getting at a value of 10. So that means obviously there is a difference, right? Again, when you are calculating the Z sample one test, you are comparing the difference between this mean and this mean. So that means critical difference at happening at 1.64, but you are 10 standard deviation away from the mean itself. So that's why there is a sufficient difference between these two. Similarly, for the BP may Z test by the p value. So if I use a stats model over here, see this particular this one is there, like BP is there given for the 10 samples maybe. Then you want to see whether the BP is of employees more than 130. Again, what you can do is you can take the mean just like that of this one, and again you can calculate the Z statistics and you can put in the formula. Other way is directly you can use this Z statistics model. So that's like this, the input is like this, x1 and x2, then value and two-sided or one-sided, and this is the code for this one. So you put the no, my x1 will be my BP directly. I'm not calculating the mean of it. What I was doing earlier, right? I was calculating the mean and I was getting the Z statistics, then the p value and all those things. Directly we're putting the data itself over here, and we are comparing with the value of 130, which is nothing about the mean which I'm comparing with. Then we get the p value and z value. So if you see that I'm getting a p value of 2. Like 210 to the minus 6, which is very small. So there is a difference between this and this. You can do the same thing by calculating the mean of this thing, then calculate the z value for what we did earlier, like this. Then calculate the z value of it, then calculate the normal ISF function for this, or maybe the CTF function for it, or you can use it directly this function, that statistics weight stats. It will take data as it is, it will compare the p-value, it will take with the z statistics and p-value for the same thing.
Vishal, what is it? 130 value 130.
130 is basically mean which you're comparing with.
Okay.
Okay, so this is like because you are given a data over here, right? This is only for the sample, but you have to
Okay.
tell something
Okay.
with whom you are comparing with, right? So this is a comparator.
Okay. Yeah. Got it.
Okay. Because okay, so this is clear. Similarly, for one test, one sample t test, you have this many in temperature of different people. You are want to check whether this. I have a question over there. I'll ask you also. This already shared in the class. This particular workbook. So there are 25 samples of the temperature. This is again a one sample. So you import the array and you define the t-test over here, the t-value defined, and then in the t-test you simply define this simply as I did in the Z sample, right? Again, you define this array as a temperature and this value to compare with 98.6. And it comes to p-value of 0.9947, which is very high. Same thing came in the class also, whatever notebook they have shared. If you see the notebook which they have shared it, this is the one sample, two sample. I want to discuss this point with you people also. Like, the same notebook which I'm just taken. So, but what happens is when they given this example, right? The same hypothesis was same. They got the same uh, p-value of yeah, p-value of 0.994 over here in the same one. But again, they mentioned that in this example, the p-value is 0.093. And I got confused. And there is sufficient evidence that prove that 16, 17-year-old boy have an average body temperature which is higher than commonly accepted average human temperature. That I got confused over here because already the you got the p-value which is very high. That means both the values are more or less same. And then you are saying the p-value is 0.093 over here. Someone has checked this thing? Ajay, Sunil, Sachin, Sunil, anyone?
Yeah, even I got confused on seeing that value, Vishal.
Okay. I also got this is right. This is wrong, right? This not should not be
Yeah,
both are same, right?
yeah. Statement is wrong actually in that.
Statement is wrong. Okay, okay.
Yeah.
Thank you. Because I also got confused. So I thought maybe I'll discuss with people on the class. Okay, so same thing. And then so this is how you're using the one sample, two sample thesis and all those things. I'll not go much more detail because you know all these things. Then one important thing is test for normality of other distribution. So there are visualization techniques also. There are statistical tests also. There are two major these things are there. One is histogram. You know, I don't have to tell you anything about that one. There's something called box plot. You people might not be knowing about this thing also. Based on this thing, the box plot also you can tell whether the outliers are coming like this and whether the function is like normal or not. You can import the box plot like this. Third visualization technique is very popular and very important is probability plot or QQ plot. So what they does is they plot the sample quantiles with respect to theoretical quantiles, and if there's a normal distribution, it will always follow the same line, all the points on this diagonal line. For suppose a uniform the distribution is uniform, then you will see something like this. And if the distribution is exponentially something like this, so if a normal distribution is there, it will always follow the same line, all the points, more or less. So this is a visualization technique. So the QQ plot, there are three kind of things are there: probability plot, PP plot, and QQ plot. More or less same thing. Slight difference is there. It's only the scale difference. If you see the difference between PP plot, QQ plot, and probability plot, difference of the scales. But show the example of theoretical values on X and Y. So these are the theoretical quantiles. This is sample quantiles. So they compare the quantile value. But the scale is normalized in the PP and QQ. That is the only difference. This is clear. Probability plot. I'll show the test this one also comparison over there. So for the quick and visual identification on a normal distribution curve, use a QQ plot if you have only one variable. And if you have many variables, if you want to visualize at the same time many, then you have to use the box plot, right? If you have to demonstrate something, use a histogram. So generally, but if single variable is there, people visualize by the PP plot or QQ plot, probability plot, whether my distribution is normal or not normal. Now, next part is your statistical test. So one test of this one is, you have heard about Shapiro test in the class, but there's some other test also like Kolmogorov-Smirnov test, which calculate the distance between the empirical distribution and the theoretical distribution, and define the test statistics supernum of those parameters. The case test is well known, but it has not much power. It can be used for other distribution than the normal. So for normal distribution is not having much power. I'll come one by one on that particular point. There's something called Anderson-Darling test. This also is more powerful than this one. This also compares the distance actually. This compares the test as whether the sample comes from a specific distribution. It makes use of the fact when giving a hypothesis underlying distribution and assessing the data. Does, like, again it compares with this one and compares the CDF function to compare whether these two distributions are same or not. One important thing is Anderson-Darling test has a better power against flatter tails. Flatter tails mean like more of a T distribution function where the tails are fat than specified. And this Kolmogorov have more power against deviation in the middle. Means if your the distribution is left skewed or right skewed, then this distribution give you more better results. But if your distribution have fatter tails like T distribution with less number of samples, then this will give you better results. The third statistics is Kramer-Von-Mises, which is in between these two tests in terms of accuracy and all. Final test is your Shapiro-Wilk test you have seen in the class. This is the most powerful test which is used for the normal distribution. It cannot be used for other distribution. This is very important. So if for suppose you want to compare a distribution, whether my distribution is exponential in nature, you cannot use the distribution. But other tests which I shown you earlier, you can use it, right? So again, you have seen this. You import the stats model, like from the stats model, you import the Shapiro, and you should use the Shapiro. Shapiro-Wilk test does not work well if several values on data are the same, and works best when they're different. Right? There are other tests also: Pearson chi-square test, Lilly-Ford test, Shapiro-Francia test. There are multiple tests for the normality and all those things. As a summary, as a statistical test to confirm a hypothesis, use the Shapiro-Wilk test, because in hypothesis testing you have to see whether it's normal or not normal, right? But when testing against other distribution, you cannot use the Shapiro-Wilk test, and you should use the Anderson-Darling test or KS test. For suppose you have to compare the Poisson distribution, or you have to compare the exponential distribution, then you will not use the Shapiro-Wilk test. Shapiro-Wilk test is only for the normal distribution. Clear?
Vishal.
Yeah.
Vishal Zyaul here. So in this visualization techniques, can you explain in this about this plotly expressed thing that we were taught in the class? No, that plotly express. So in this visualization technique, so that plotly express will also come.
You can use the plot. I'll show this. I'll show in the Python Excel. I'll show the Python example for this one. I have actually included. I'll show the Python example for these things. Okay. So probability plot, what it does, it compares the next I'll show the example itself in the Python. So it compares this probability plot also in Shapiro test. They compare with the normal distribution. So again, that's for Shapiro test.
Vishal, sorry to interrupt. Yes, the Shapiro test in sample, right? It's always normal distribution, correct?
Come again.
See, Shapiro test we are applying only sample, correct?
Correct.
So sample distribution always normal distribution.
Not necessary. You know, the sample size is lesser. The sample distribution may not be the normal distribution. No.
So
Normal.
for normality only, we need to do the Shapiro test.
Correct. For normality only. Correct.
For normality purpose only. That's it.
Correct. For normality purpose.
But based on the central tendency theorem, whatever sample you are taking, so your distribution is a normal only.
Okay, I'll show you one thing. So what I'm talking about. So for suppose this is your sample. Correct. This is total population. Out of this total population, this is your sample. So do you think this sample will be normally distributed if I plot this? Increase the number of bins over here. Do you think this is normally distributed?
No.
The samples, they're not. And if this is sample mean, right? This is sample mean of this distribution. Oh, sorry. My mistake. I could show the wrong thing to you. 1 second. Yeah. What happened? Sorry. Yeah. So what happens? I'm taking a sample from a normal distribution. Now let me take a sample from exponential distribution. Okay. Let me show you the impact of that thing. Maybe the function is exponentially distribution, correct? I've not used it, so let me check. Exponential distribution of x lambda. Right, I'm using, instead of this, let me just copy this formula somewhere here. Instead of this, I'll use this now. Okay, can you see this? This is left skewed. Now the sample. If I further decrease the sum, can you see this? If I increase the formula,
Yeah, I can.
Yeah. Let me directly put this formula over there only. Because earlier I was using a normal distribution, right? So you were right. Can you see this? I've taken the 5 samples. Now the sample mean is left skewed.
Left skew or right skew?
Yeah, sorry, right skewed. Sorry, right skewed.
So right skew, yeah.
Correct. Can you see this?
Yeah.
Earlier my distribution was normal, so you are getting a normal distribution. Now this is since the sample size is smaller, okay, I'm getting a right skew distribution. Now if I increase it again, let me show you again the increasing of this one, right? Let me increase the number of sample size. Same distribution, I'll show you and how it changes. Can you see this become normal? Sorry.
Yeah, got it.
Right? Became normal.
Yeah.
Now that function which I used over here is not very highly exponential. If that function is very highly exponential, no, in terms of this one. See, if it's very lightly exponential, right? If I increase it very highly exponential, again I need much more samples to make the sample mean distribution as normal distribution. Correct?
Okay, Vishal, I got it. Yeah.
Got it? Sure. Okay.
Yeah.
Vishal, Shunil here, Vishal.
Yes.
I read one thing in Safiro test, when the values are unique, then it will give a good result. But
Correct.
if the values are having ties, then the most preferred one is Pearson omnibus test, which is nothing but the normal test function under stats. I read this in one blog. Is
I
that
have
right?
mentioned the same thing. Yes, yes. I have also
Okay.
mentioned the
Okay.
Shapiro well test does not work well if several values in the data set are same, and works best
Okay.
the data set with works best for a data set with less than 50, but can be used with large data set. So if the number of values are same, it will not give you the good results. That is true.
Okay. Okay.
Okay.
Yeah.
So
Thanks.
again, yeah. Again, I was coming back over here. So the null hypothesis for the Shapiro test is that both the distribution are same. It's in a Shapiro test, again it calculates the p-value and it compares the normal distribution. That's why the null hypothesis, when you get a very high p-value, then you say that the distribution is normal. Because I told you right earlier, when the p-value is high, the two things are same. When the p-value is smaller, the two things are different. That's why in the Shapiro test also, when these two things are same, you get a very high value, then you say, okay, this distribution is normal in nature. Got it? Am I clear? Okay.
Vishal, can you repeat once, Vishal, on this one?
So earlier what we said is, if the two distribution, if the sample means of two distribution are similar, then we'll get a very high p value. If you see in the test or two samples and all, when you compare these two sample t tests, when you get a very small p value, then you say, right, these two distributions are different. Correct? Correct?
Yeah.
You
Yeah.
do these two sample t test. When you get a very small p value, then you say this, okay, these two samples are different. When you get a very small p value, so that means p value tells you the probability of things being same. Correct? High p value means the probability is very high that these two things are same. Similarly for Shapiro test also, it compares these two distribution. It compares, because we don't have any other sample, it compares to the normal distribution. If the p value is very high, that means the distribution which you are comparing with is the same as normal distribution.
Okay.
Okay. If this p
Yeah.
value is very small, then you say, okay, it's not normal distribution because these two things are different. That's it. As simple as that.
Okay.
And probability plot also, the quantile function, it calculates for the normal distribution, and it calculates a quantile function for this distribution and compares these quantile distributions. Okay. So you can read more about it online. What is quantile? Basically, when you divide each and every segment, so that this is a example of quantile. Each of any set of the value of variate, which divide a frequency distribution into equal groups. So like for this example, each and every group is divided by 10% segment. So 10% values, 10% probability value, 10%. So like x1 minus x2, if you calculate, you get 10%, 0.1 for this case, right? So the probability plot, this is basically a theoretical quantile for normal distribution, and then you calculate for the your sample distribution. Now let's see this example in Python. So I have considered a prima India wala case, which is already shared with you, right? This is the case, probability plot was there, right? Now let us see this diabetes column, which is there, right? So this is just a dist plot, simple dist plot, which is this distribution plot, right? If you see, this is right skewed distribution. Probability plot is nothing but simple. You put stars or top plot, input data. Input data is my this one only, the diabetes degree function, right? Plot equals to PLT. Now what it does, simple one line code. See this thing, correct? So this is not a normal distribution. You can see from distribution plot also, it is more of exponential kind of thing, or a right skewed distribution. Same thing you can find over here. Correct? Clear? So this follows like this kind of distribution. So you can say if this was a normal distributed. So for suppose, let me compare with BMI, or maybe BMI. Okay, BMI seems good. Let me put BMI. Let me run it first. Not running it. BMI. Can you see this? More or less all the plots, this is like a normal distribution, so all the points are coming like this. This is a bimodal, so this is creating some issue over here, but if you see, all the points are coming like this. Clear? This is how you visualize.
Yeah.
Very simple way to visualize this thing. Probability plots. I'll come next because multiple 60-70 slides are there. Now, in case your normal the distribution is not normal, then what you will do? Very important point. So in the t-test to check for differences between two groups, the data comparing has to be transformed. You cannot simply say that there's a difference in the two groups means when you're transforming the data and then you're comparing, then it's become difficult, right, to compare. Because for suppose this is right skewed, you have seen in the class, when it's right skewed you put a square root function or maybe log function highly skewed, and it's a left skewed you put a arcsine function, log function, different functions you apply, right, manually. Earlier we saw, right, square root, square, exponential, log, and all those things. We do it, but the thing is, for significant for analysis like F-test or T-test family of test, independent and dependent samples and all, well, violations of normality are not usually a death sentence for validity. I'll come on that particular point. As long as the sample size exceeds 30, even better it is more than greater than 50, there is not usually too much of an impact of validity of non-normal data. Something that Stephen says, and what it means, what is saying in this sentence is, if your sample size is quite large, right? So what happens? The central limit theorem gets applied, because at the end, the sampling distribution of sample means should be normally distributed, not the data itself. So if the data points are more than 50 or maybe 100 and all, then you don't need this test, the normality. Already the central limit theorem will apply, and the sample means will be normally distributed, right? But again, let's see if you have a small number of sample and want to do it. So there are different methods to transform into normal. Okay, we are okay. So one is box cost transformation. So box cost transformation is convert the non-normal data into normal data by raising the distribution to power of lambda. The algorithm can automatically decide the lambda function. So what is lambda value? I'll tell you. Box cost transformation is a statistical technique known to have a remedial effect on highly skewed data, blah, blah, blah. The lambda parameter of box cost has a limit from -5 to 5. Okay. So this is a lambda distribution. For suppose, so it raises to power to 2, right? Or raises to power to lambda. So for suppose, lambda, you have a lambda power, lambda ki value -2. So lambda ki power -2 becomes 1 by y square, right? Y ki power -2 becomes 1 by y square. Similarly, if the lambda value is -1, that becomes y ki power -1, which is nothing but 1 minus 1 divided by y. Similarly, for 0.5, it becomes square root 1 become y directly, y lambda ki value 2 becomes y square. So it automatically determines this lambda value and it transforms the data for you. Okay. One important parameter is all the data should be positive and greater than 0. Very important. If your data is not positive, you cannot use the lambda box cost transformation. Okay, and any value is 0, then you hello. Hello. Okay, so So this is box Cox. It works like this. So it calculates the value of lambda. So how you will do this? So the output of this is two things. One is transform function. Second is the lambda value, because you need this lambda value to convert it again to the normal thing, right? So first you import the stats module, then you calculate you apply the box Cox transformation, you get the transform data, you get the lambda value. Then again, to get the data back to normal, you use an inverse box Cox transformation. Okay. Xt is a transform data and lambda is a parameter. Anyhow, I'll show you. Now, second way of doing it, the power transform in the sklearn. So currently, power transform support the box Cox transformation and geozones, and there are two transform. Box Cox I shown you right earlier. I'll show the geozones also. So it calculates. You have to define the method, and based on it to transform the data. Box Cox require the input data to be strictly positive, while Geo Johnson supports both positive and negative data. It's very important. By default, when you're using the power transformation, the zero mean and unit variance normalization is applied. So you don't have to scale the data. Sometimes what happens, the data is very highly outliers and all, then you have to scale the data, then you have to use it. In box Cox, you have to scale the data, then you have to use the transformation. In power transformation, automatically it's the scaling is done, right? So this is Geo Johnson, more or less same thing. It also calculates the lambda value and all. In box Cox, you have shown you already this thing, right? Both the method transformation is parameter is lambda. I've told you this thing also. So how you do this one? Pre-processing the power transformer method में box Cox or Geo Johnson. You define that method which you want to use. I'll show you that thing also, how I transform the data. So let's see the Python code for this thing also. People are there. So is it okay? I'm like, or it is not up to the mark and all. Am I clear on the things?
Yeah, Vishal. For me, it was
Yes,
good.
Vishal.
Yeah. So
Yes,
let's see.
it's good.
Okay, thank you. So let's see the same thing, whatever the data which we have PMI and this one. So let's import the power transform. Okay. Then apply the Geo Johnson, because some values are over here zero also. If you see the data, some values are some zero and all those things. We cannot apply that, right? In the zero, the box Cox we can apply. I don't want to transfer scale the data or add some values and all. So I'll directly use a Neo Johnson and all those things. So in this case, standardization is true. We can make it false also if you don't want to standardize the data. Okay, then you put the transformation on the data, fit.transform. Then again, I'm converting the data into data frame, because you need the values, because this columns also will come, right? It will get confused. So we have to remove this columns, only we need to get the values. Then we have to apply the transformation like over here. So we define the transformer first, then from the data we extracted the values only, then we apply the transformation on the data, then again we converted data into data frame and put the columns back over here. Okay, now let's see the histogram and what has been done when you applied this things and all those things. And tell me one thing, this normalization is very much required or not required for this data? Should I do? Should I check the should I do the normalization, because there are 68 data points are there in the row. So shall we use the normalization or not? First of all, this is a very important question. The number of rows, the number of data points which are there. There are 768 data points. There is 768 rows, right? For each and every column. So normalization is required or not required? First of all. Hello.
Yes,
Ah,
it's required.
yes, Vishal, we will be needing the normality actually.
Okay, I'll show you something, then you'll understand what is actually happening. So after this, applying the transformations and all, let's run this. I use this diabetes pedigree function right now. Let's plot it, right? Let's run this. Okay, what happened? Okay, I've not run this. Let me run this first. Okay, see this thing. So this was your earlier data. After normalization became like this, like histogram. If you see the PP probability plot, it was like this. It became like this. Can you see this? This is transformed data and this is original data. Similarly for this histogram, if you can see also histogram, this is an original data, this is transformed data. And it is standardization has applied, standard normal scale. And this is the data. If you want to see the data, it became like this after applying the transformations and the data. Now let's see one more thing. So I guess, yeah, let's see how we can, from this complete test data which is available and this transformer, if you see, when I applied this transformer, I applied on the complete data. I don't have to go do column by column. I can apply the transformation on the complete data itself. So here I just remove the last outcome column and I completely applied that transformation over here. If you see, can you see this?
Here the question,
Yeah.
Vishal, say if each attribute will have a negative values, right? In this case, method will vary.
No, so that's what I'm saying. Power transformation, it automatically calculates the which lambda value is required for each and every column. We don't have to specify it. So here when I define
Okay.
the method as Neo Johnson, it's not box Cox. Box Cox is prone for the zero values and negative values. I'm using Neo Johnson, which is independent of that. It can take the negative values also and zero values also. And for each and every column, it will apply something different lambda values. I don't have to worry about it. For each and every column, it will try to fit the data to normal distribution.
In
Okay.
this case, if I use another method, then I have to go with each and every column.
No, box
If there
cause
is a negative
also,
value.
no. Power transformation, you can directly define the data. If you don't want to do
Okay.
it, then this data, you can define that as a column. For suppose some column you don't want to touch, right? Then you just put that data right over here, the column which you want to specify. I wanted to convert the complete data to this one, normal distribution. I directly defined it. And this is Neo Johnson, Syed, again, this is not, it's independent, it's not depending on the zero values or negative values. It can tackle both.
Okay.
Okay. When I define this method, I only define the method over here. If you see, applying the method I'm doing over here, pt.fit.transform. I'm just defining the method as pt and the pt.fit.transform applying on the data over here. Data may complete data I'm taking, complete data, only the outcome, last outcome value I'm not taking. That's it. So complete data itself I'm putting the transformation. And then again, complete data I'm converting to data frame.
Okay.
Okay, so I don't have to worry, like it will automatically take care. That is the beauty of this one. I don't have to do it individually for each and every column. It will estimate by itself. If you see this, I mentioned the PPT also. The optical parameter for the surface variation minimization is estimate through the maximum likelihood for each and every column.
Okay.
Okay, yeah. So now let's see. I mentioned one more thing. That's the so let's see. This is a scale data. Now let's see. We can make a for loop, right? For understanding which out of this all these variables, which is a significant this one. We can apply the two sample teachers and all those things, right? So let's see that thing. So whatever you have seen, I'm making a dictionary, probability value empty dictionary. Now for all the values, all the columns, one by one I'm iterating to. So one column is diabetic, I'm defining when my diabetic is 1, diabetes is 1. Non-diabetic I'm defining is when my outcome is 0, this last column, right? Then I'm calculating the T stat and P stat for this particular column. For suppose first case, this will be pregnancy. So it will run for pregnancy. Then I'm calculating the P value and T value, right? Then I'm updating my dictionary. So for pregnancy, my P value will get updated. Similarly, I'll run for the glucose. My P value for the glucose will get updated in the dictionary, right? Now what I'm doing is next, I'm just making a significant features empty list. Now if my P value in that dictionary is less than alpha, I have defined alpha as 0.05, it will update my list. Otherwise skip it. So if I run this, okay, 1 second. Yeah, if you see this, I'm getting a P value corresponding to each and every column. So P value for pregnancy, P value for glucose, blood pressure, skin thickness, insulin, BMI, diabetes, degree function, age, and all. Right? But out of these all, where my P value is less than 0.5, it will consider significance based on this loop. Because here, insulin and skin thickness has a higher P value. I don't want to consider as my significant feature. It's not impacting my glucose, it's not impacting my diabetes. So based on this, I'm filtering and again I'm generating a new significance feature list. Now let's see if you're comparing with the transform data t-test. This is, I just calculated this one. Now again, let's see with the transform data complete thing I put it now with the original data also. This is transform data I showed you, right? Now this is the original data. If I run with the original data without transforming, if you see more or less, I'm getting the same columns. Can you see this? Pregnancy, glucose, blood pressure, BMI, diabetes, age. Similarly, also here, pregnancy, glucose, blood pressure, BMI, diabetes, and age. Can you tell me a reason behind it? When I use a transformation and I use the original data, I'm getting the same significant features. My P value is not being changing drastically with respect to that, the transformation, more or less higher value for the same again. So there is no impact of major impact of transformation. Can someone tell this why it's happening? Hello? Anyone? Please, let's discuss, no?
So what was the question?
So what I'm saying is when I run this data, right, I put a loop. I calculate the P value for each and every column, diabetes versus non-diabetes. I want to see whether that particular column is impacting my diabetes or non-diabetes. So first I run that code on the transform data. Second, I run with the original data. So the significant feature which I'm getting in the original data, the P values and all, is same as with the transform data also. So somehow the transformation is not changing my P value or my significant column.
So you mean to say we are getting the same P value
More or
post
less same,
transformation
yes,
as well?
yes, more or less same P value we are getting it.
So if the observation is few, then it will not change. Does
Yes,
that mean like that?
yes, yes. So same thing. Like again, go back over here. We saw this, right?
Yeah.
As long as the sample size is 30 or maybe higher, then you don't have to convert to normal because central limit theorem will apply on the standard this one, and your sampling distribution of sample means will follow a normal distribution. It's not about the data which is normal or not normal. It's the sampling distribution of sampling mean is normal or not normal. When we checked over here with these things, we checked the data is normal or not normal. We made the data normal. Correct? We checked whether get
Is 30 is a threshold, or if saying for example I have a 38 or 37
it can be high.
is
That's what
sample
I'm saying.
size.
50 is also okay. 100 is also okay. That depends. That's what I'm saying. That maybe 30 is a threshold. This is given in all the test books and all.
Hmm.
And we saw that also when we in Excel sheet when I increased to 27. The sample error is matching with that sigma by root n, right? But here your call number of rows, if you see the data point is 768, something 768, right? Very high number of data points. I don't have to check for the normality and all. I can directly put the hypothesis testing because number of data points are very high. I don't need the normalization. I will just want to show you how the normalization works and all those things. That's why I use, if the number of data set is very small, you might have seen this thing. I try to do in this also. This temperature data, there are 25 data points, right? See the probability plot for this. Let me show the probability plot for this one. Where 25 temperature data points are only there. Let's run this. Okay. Put the probability plot over here. Yeah. Can you see this? 125 samples are there, but which is more or less okay, normal. And that's why you're getting a p-value also. If you see the p-value which you get out of it is somewhere around 0.33. No, sorry. The p-value for this one was 0.994. So 1 minus, you have to calculate that thing. The p-value was very high over here. The sample was similar to this one. The temperature data which was there for the boy is 98.6, right? And the distribution, if you see of this data distribution, if you plot this distribution, it's like this. The probability plot is like this. So you do this normalizations and all when your data samples are quite less. Otherwise, it's not required. Am I clear or confusing you? Please.
Yeah, I'm clear. Yeah.
Correct?
Yeah.
So you have to be very clear if you don't apply this normalization techniques if your data size is very high. Not required. Clear, people? Many things are there still to be covered. I don't know. Okay, this I have showed you already in the. Okay, time is very much okay. I'll run through now.
Vishal, so based on the normal distribution, if the data are normal distribution, then we will be using the parametric statistic techniques, and if it is not normal, obviously we'll be using the other techniques for non-parametric statistics, right?
Selva, actually, if you see, this is not a data which is normal or not normal. If you see the condition, when we talked about the condition of p-test and t-test, right? The sampling distribution of sample mean should be normally distributed.
Okay.
It's not the data which is sample, which is, it is sampling distribution of sample means. It's not the sample which is normally distributed, no. The sample is for sample means. If this is true, if our parent population is normal or if our sample is reasonably large, automatically if your population is very large, the central limit theorem will apply over there, and automatically become the sampling distribution of sample mean will become normal automatically. This is very important point which you don't get very easily. That when you have to apply this, whether your data should be small or this one and all. So you don't have to apply when the data set is quite large. You don't have to apply this normalizations and all for hypothesis testing. You need to apply this for the regression and all, but you don't have to apply this for the hypothesis testing. Because central limit theorem is coming into play, which talk about the sample means. Correct?
Yeah.
Okay. These are the very fine things actually, which was not covered in the class also, and I also read a lot of links I have read, and based on the Excel practice and this, when I saw this by myself Python exercise, I tried to do this and transform data and original data. I also got confused and I searched and I understood based on these things. Okay, the data is not important. that way. The sampling distribution, the sample mean how they are, whether they are normal or not normal, that is important. If your data is not normal, because if you remember the stat quest and all those things, the link which he shared, even if you use a exponential like this one I showed, right? If I use exponential data also, and I put the sample mean over here, I get a normal distribution, even if my population is exponentially distributed. But my sample mean, if you see, it's still normal distributed, even with 8 number of sample, if you see in this case, because this is not very highly skewed data. Am I clear?
Yeah, sure. Yeah,
Oh,
it's clear.
okay. So ANOVA test, I'll just quickly go through it because already we are multiple things I wanted to cover. So when you're comparing the mean of two groups, two or more groups, these things you know, I will not. So one important thing is when the two distribution overlap with each other. So individual means don't differ by great margin. Difference between the individual mean and the grand mean, mean of this and mean of this together, mean of this grand mean. The difference between the individual mean and grand mean will come somewhere over here, right? The grand mean of these two means will not be very different. But in case of the two distributions are very different from each other, right? The grand mean will be different from each individual means. Now, one important thing is why it's called analysis of variance. We are checking the means of two or more groups, right? Whatever testing we are talking about, sample distribution of sampling means, t-test, z-test, ANOVA and chi-square. We are only talking about the sampling means. Then why it's called analysis of variance? It should be analysis of means, right? In that case. So why it is like this? Because they check a f-test and all. So I'll give you, they compare the variance of these things. So how it is, the ANOVA test compare the within group variance between the between group variance. So for suppose this is a variance, this so within the group variance is larger, within the group variance over here, if you see, right, this very higher, and the between group variance is smaller, so f value will be smaller, reflecting the likelihood of no significant difference between these three samples. What it means is if the sample, the variance of this chart is very high, I'll use a pointer somewhere. If the this is very high, this is also very high, and this is also very high, then the possibility that the values will be from a same distribution. If their within group variance is very small, for suppose if I use a pen over here, if it's like this, if it's like this, and if it's like this, sorry, then the possibility of these three variables being different is quite high. But if they're very large like this, the variance, right, the possibility the samples which you are checking it may fall on the same this one, the difference you will not be able to find it. So that's why this is called analysis of variance. You compare the variance within group variance and between group variance. Okay, so type of ANOVA test, one-way ANOVA test and two-way ANOVA test. I'll show you one-way ANOVA test and what is two-way ANOVA. So for suppose this is normal bone density, one person has osteoporosis and osteoporosis. So when you're comparing these three categories and you want to compare the mean of this one again like this is called one-way ANOVA. One is only one independent category which is there, right? But when there are two independent category, for suppose this is there, which is depending on this one, then for treatment B, these samples are given, for treatment C, this sample is given. Then this is called two-factor ANOVA. There are two independent variables on which the system is depending. So this is called two-factor ANOVA. Okay, practice sets I'll show you later on. Then again with replication, I'll just run through it because ANOVA again, maybe next time we'll take it again. Then so ANOVA test will only tell you whether the difference is there or not there, but will not tell you how much difference is between each group. Then again you have to run a post hoc test, post ANOVA test, like Turkey multi-corpus test, Turkey's test, which will tell you p value for each combination, one combination, second combination, third combination. Based on that, you decide which value, which significant difference is coming from where. So that is called post hoc test, post ANOVA test. Like these three tests are important for that one. Now chi-square test, I'll come on that one. So there are majorly two type of chi-square tests. One is for the goodness of fit, and when you demand sample data matches the population. Second is chi-square test for independence, compares whether two samples are having the same distribution or not. So very small chi-value test means that you observe data fits your expected data extremely well. I'll show you why. So this is how the chi-square is defined: observed minus expected upon expected. So if this difference is very small, right? And the summation, this difference is very small. The chi-square will be very small. That means the observed data and expected data both are same, right? So both the distribution are exactly same. When this is very high, that means there is a huge difference. Now, expected means what? Expected frequency consider there is no difference between two sample in question. I'll tell you in detail on this also. So what is the chi-square distribution? Chi-square random variable follows a chi-square distribution. It can be written as sum of squared standard normal variable. So this is, Z is a standard normal variable. If you square it, you get a chi-square distribution. Degrees of freedom is nothing but n minus 1, number of rows minus 1, number of column minus 1. Let me go through because already time is, so I'm running through slightly. Assumption of chi-square test important. The chi-square test assume the data for study is random. You know that thing. The data categories are mutually exclusive. The data should be in the form of frequencies or count, not in terms of percentage. That data should not consist of paired sample. Paired sample means the one observation should not be depending on other observation. Then again, the chi-square distribution, if the number of degree of freedom is higher, it follows a normal distribution, becomes like this. If the degree of freedom is quite less, it follows like this. This is with 4 degree of freedom. With higher number of degree of freedom, it follows a normal distribution kind of thing. So let's see an example. People are getting late, or should we round up, or should we carry on? Or shall we
Can you take a one more? Next time.
Still one probably.
Can next session, huh?
Yeah,
That would be
because you are running through, no?
yes.
Instead of running through, we can have one more session to it.
Correct. So what about other people?
Yes, Vishal. I mean, if you have it, another session during the same time, I mean, on Sunday itself by 11 o'clock, then it will be really very appreciated, because I think we have more to go. I mean, we are just in 24-25 slide. We have a lot. So I think our next session will be good for us.
Okay. And is this the things which I'm discussing, is it useful or not that much required?
Useful. It was useful.
Yeah, it is useful, Vishal.
Yeah.
Yes, Vishal, it's good only. It's very useful, right?
Okay, so I'll just give you a brief what I'm going to take in the next about PPTs anyhow. So this I'll give you the chi-square distribution and example of what is chi-square, what is contingency table, and all those things, because you have two kind of chi-square, right? Then example of chi-square, what is chi-square table, so when to use which. And advanced topic I was about to discuss about the sample distribution of sample proportions. This you're going to cover, like it is going to use this in your assignment also. So right now what we have seen, I'll tell you brief about this one. So far what you have seen, when you have a discrete continuous variable, that's why you do the sample distribution of sample means. Mean is only possible for a continuous variable. For suppose you want to compare the votes when you do the actual test, actual voting are done and the exit polls are done, right? You get a sample and you ask them which party, how many votes are getting, you're giving yes or no, right? That kind of category you got it, 0 or 1, 0 or 1. So how do you, based on the categorical counts, how you convert to the actual results, which has not been covered in the class also. So because for suppose if you ask only about the BJP, if you ask these people, are you going to vote BJP, yes or no? So for suppose 10 people, out of 10 people, 5 people said yes, I'll vote for the BJP. Based on this can you say something about the population? This is called sampling distribution of sample proportions, because we are getting proportion. 50% people here are saying that they will vote for BJP. But can you say the same thing? You cannot apply a 50% directly over here, right? That is how the sample distribution, sample proportion come into play. Here your binomial distributions and all come into play. So because any counts which you have seen, right? So maybe I'll take in more detail. The binomial distribution comes into play over here, because binomial distribution is a distribution of counts. Then again, based on that, you have to calculate what is my distributions and all, how this is distributed. Then again, you have to calculate the sigma value and the p value. The mean value and the sigma value is quite different. You have to use the binomial distribution function for that. And then based on, again, if this is normal distributed, the sample distribution of p is normal distributed, then only you can apply. And there's a condition for this, whether this is normal distributed or not, right? Then for suppose this is a vote count, then you see that whether it's normal distributed or not. Based on this, you apply this one based on the z value and all those things. There are multiple examples I want to cover and all those things. And then for two samples, sampling proportions, there are three samples and all those things. Then parametric versus non-parametric test, what are non-parametric tests and all those things. So what are different this one non-parametric thing, what is Wilkinson test, then measure of skewness. So when this one is when you have, because skewness question is there in your assignment also, I guess. So just this code you can remember, just import skew, or for the df.skew, you'll get the skew value of the data, like category, the variable which are in question. So df.skew, you will get the skew value. I'll cover in more detail these things. Then spot endings and all those things are there. Then chi-square test for feature selection in machine learning and all those things are there. So multiple things are still remaining, I guess. Uh, so this is something wanted to cover and all. But actually, we got into more depth, so I could not cover much. I thought I'll be able to cover it. So how's this one? People, any
Vishal, can you please share this slide and Excel sheet?
Excel sheet, I'll share it, Sayed. And slides I'll not share right now. Okay, because I have to update the things, and I'll share a Word documents and all. I'll share all the links in the Google Classroom also. Whatever links or snippets are there, right, which are required right now, I'll share in the classroom, in Google Classroom. I'll share it over there.
Okay. So whatever cover is so far, you update, please share it with me.
Yes, I'll share
with the group.
Sure. I'll Google Classroom and I'll update these things, and I'll update, because more than 50-60 links are there which I have studied, and everything, if you see, it's in the snippets, right? In the bottom, I updated whatever links are there, I've gone through and all. So there are multiple links which are there for each and every section. So I'll update these things. And one thing I'll give you right away, I'll share this PDF also about the multiple tests which are there, talks about the maths of those tests and all. So this is all, team. It took me around 2-3 weeks to cover this much. I had to, but I request, please, like other people also can take a session like this, and don't take much. Maybe even if you're taking a single topic, for suppose any topic you choose, and give a session to other people, it will be very helpful for other people, because in the class you are not covering the things in very detail. We are covering the very surface level, but if you go in deep, the things are very much deep inside. Selva, Sachin, Ajay, Sunil, what do you think?
Yeah.
Venkat, the people. So I think the things are very much deep. We are only going the surface level. If you, I think you might have seen it, right?
Vishal.
This one, like things are very
Vishal.
deep.
Yeah, before saying that, now can I say something? Whatever the topics which you are going on is that because we are in a different program which we have both ML and AI, ML and AI, but if you go into different parts or different course, no, the details which you are taking right now, they will be taking in it. But right now, what they are giving us is an high level only. And that high level, when we try to do it in a modeling, I think all the transformations, whatever you discussed right now, it will be covered as a part of that.
Okay.
Because when I
Anyhow,
heard from different people, okay, they were saying is that it's a combined program. They will take first high level only. But if you go with the individual program depth, if you take a data science, it's a complete vast. Whatever the depth right now you are discussing, it will be there in it. Because that purely on data which we analyze on it.
Okay. Okay.
But for the front end, for us, it will be a kind of a UI only. Back end, we never think of it.
Okay.
Yeah.
But I was thinking that, see, if we can divide the things, like some topic someone can take someday, and in between big day also will work, I guess. Even if you're taking
sure.
the topic, someone is taking simple distribution also and taking maybe 10-15 minutes also, no? Because the things are very deep. So even if we are dividing and combining the things and we are teaching each other, not a very good thing. I just want to say at the end this thing only, maybe because something's not clear to for me also. So if I tell you if I tell you this, if I take the Shapiro test also, right? So if you take the Shapiro test from a Pima India setup, you will get a value of 0. Earlier I was struggling with this one, why I'm getting a 0 value for Shapiro test. But later on I realized that since my sample size is very high, the sample distribution of sample will always be normal, exactly normal. I realized this very late. I was getting constantly, if I show you this thing, the Shapiro value, any column which is there, for suppose if I run this, I get a p-value is very 0. So exactly normal. Right. So already that distribution is normal in nature actually. Because sampling distribution of sample mean, because of very high number, I was struggling a lot for this one. But if
one second, the Shapiro test is basically to check whether the sample distribution is normal or not.
Yes.
If I'm not wrong.
Yes. Not the sample. But it's very important.
Sample No, I'm taking take an example. You have a population. From the population, if we take a sample, that sample which we take from the population is normal or not.
Correct.
The subset of it is a Shapiro test.
So no, it's not taking the sample. Again, I'm saying Shapiro test checks whether the sampling distribution of sample mean is normal or not normal.
Yeah.
It's not the sample which it checks. It checks the sampling distribution of sample.
Can you please come again? Sample mean?
I shared right over here the conditions for the TFS and G test.
Syed is basically the sample which we take, the distribution of the particular sample and the mean has to be normal.
This particular point.
Okay.
Yeah. The sample mean and distribution has to be the same.
The sampling distribution.
Not the same.
Mean.
Should be normal.
Mean one that Vishal showed in the Excel, right?
Yeah.
So that part.
This part.
Okay, got it.
The sample may not be normal, but the sampling distribution of sample means they will be normal. Even if my sample is left skewed, right skewed, blah blah blah, and all those things. Population also might be something else. But my sampling distribution of sample mean should be normal. This is how the Shapiro test is checking. It's not checking the sample, it's checking the sampling distribution of sample means. This is very important. This something I struggled a lot, like, to be very honest with you people also. Yesterday also I was struggling why I'm getting a Shapiro value of 0. It should not be 0. And this something is not being covered. This should be something should be covered. So also he was saying it will be covered in other classes and all, but at the end we have to apply this thing, right? So where the Shapiro test was. Yeah. So that is very important actually. Okay.
Vishal, are you able to see the chat box? I mean, are you able to check the chat box?
1 second. Yes, I can see now, but nothing is there.
Yeah.
1 second. Matplotlib import warning. So warning wala, yes. So warning wala, I'll tell you what is basically warning thing. Okay.
It's those red lines, right? That.
No, okay, I'll run this one. I'll show you. For suppose I'm running this pair plot, right? It will take some time.
Okay.
So this kind of see warning I'm getting it. There is this kind of warnings will keep on coming on the Python because they tell you something. Okay, this is something that it will run also. It will show the pair plot. So first is given the warning, then it show the pair plot also. Still running.
Okay. So to remove all this errors and warnings, we use
Yes.
that.
Unnecessarily you don't want see that is something they're not useful because already the things are running for you. So
Okay.
when you think that this is not required, this warning is not usable, it's always will be there unnecessarily this is coming, then you can remove
Okay.
this. And just so you have to import the warnings like this.
Okay.
So you have to import the warnings over here. Okay, just import that. There itself you can do it. Then you do the you just remove the warning dot filter warnings, ignore category. There are two categories, three categories which I have seen. I use the future warning, it worked for me. So I ignore the warning which is coming over there. So for all the future categories which are coming, it is removed. If I run with this now, maybe again it will take some time. So the warning will not come.
Okay. So that ping box with the warnings won't come, and
Yes.
just the output will be
Yes.
coming.
Only I don't need the warnings, right? So
Okay.
one second, I have to run this. One second. I have to run this first. Then I have to run this.
Fine.
That's the only difference, Joel. So we
Okay.
did the warning.
Thank you, Vishnu. Thank you.
Okay, team. So I'll plan for next session sometime again. Or cover the remaining part of it, whichever I have shown you. And if something you find it something I have told something wrong also, that is something maybe you might feel that something is wrong, please discuss and put in the group something if something you find that something is not right by my side. Because as you I'm also learning, right? I'm also not an expert in this. I'm just learning and discussing with people. Hello.
Sure,
Yeah,
sure.
Vishal. Yeah, sure.
And yeah, please keep on discussing. Please, in the Google Classroom, please keep on sharing on the articles which you are reading and all. Please share the things over there so that there is a track record and people can go and check it in there, so they can read about it.
So Vishal, what will be you will be sharing now? Like the Excel, the
Excel I'll
PDF,
share,
and the
Python code I'll share what I have done.
okay.
Okay, and
Okay.
I'll try to share the small some important snippets which are there. For suppose this anyhow the
Yeah.
basic thing, right? So this condition I'll share for you. This anyhow you have it.
Especially related to the test. Yeah. This the test
This
that you have mentioned, right?
I'll share this one, not an issue. This I'll also share something. This I'll share it with you how to import, and
Hmm.
this I'll share a snippet. I'll share it, and I'll share this Shapiro wala.
Yeah.
I'll
This
share
one.
with you.
Yeah.
Yeah, this I'll share with you. So whatever something is relevant right now, and at the end I'll make everything in a Word document. I'll share in the Word document so that everything is in proper format. Okay, I'll
It's
share.
not good. PPT also fine, Vishal. Don't waste your time.
No. Actually, there are still
Yeah.
something glitches are there in the PPT. Multiple things and multiple order they are. So that is the reason.
Okay.
So
Vishal, in Safiro, I have one doubt, Vishal.
yeah, tell me.
Even while doing the project, also, I just got confused with that. So in Safiro, science shared one file, right? Statistical test one
Yes,
file he
Acha,
shared, right?
I want to discuss that thing also. It's very important that you raise this point. So this is the statistical test. If people have not seen it, please see it. Cyan has shared all the statistical test over here. Okay, please carry on. Sunil.
Yeah. So in the Safiro test, he mentioned like if the p value is greater than 5%, then it is probably Gaussian, right?
Correct.
So in the project data set, when I ran that in visualization, I could see the data is normal, but when I ran this Safiro test, I used to get values less than 0.5, probably not Gaussian. So uh, whether it's the right way to say that statistically the data is normalized. Is that the right way to use this one, or is there any other techniques we can show that in statistical way?
So if you check the frequency, one problem with the Shapiro test is the data is multiple times same, right? We discussed this point also.
Yeah, I tried with normal test as well. In normal test also, normal test function is there, right? I used that one also. That one also showing values less than 0.5.
Normal test.
But yeah, but here if you come to the second next line 29 or something, he has given that normal test example as well.
This one.
Yeah, K to normality test. So using this also, it's showing values less than 5%.
For which data, for which category you checked it?
One second.
Because I have yet to start the assignment today. I'll start it. I have seen the questions and all, but I have not seen the
Okay.
data. Maybe today I'll start and come back on that.
Which question you are referring, Sunil?
One second. I'm just taking that one.
You can share your screen.
Okay.
So
I'll share my screen. Yeah.
How can I disable? Okay.
I'm not sure whether I'm doing right or wrong, but I need to clarify this point.
Sure.
I'm not able to share my screen.
1 second. Let me check how to do it. Maybe I have to make a host to you. 1 second. I'll make you host. Make host. Yeah. Now you can share your screen.
Yeah.
Vishal, you stop sharing, then he can share.
I have stopped
Yeah,
sharing.
I'm
I
sharing.
need to make them host.
Yeah.
Hello. Can you see my screen, Vishal?
Yes, we can see your screen.
So, so here is where in under, I mean, question 4B. So 4B, I just separated the BMI of male and female. So I just want to check whether the normality of BMI male and female are the data is normal. So on running a distribution plot, I could see it's normal. But when I run the normal test, it shows like probably not Gaussian, and the value is like 0.005. So visually, I could see the data looks normal, but when using the normal test function, the p-value is less than 0.5.
Can you, okay, 1 second.
I'll show you that function.
No, that is okay. Function might have made right only. Okay, well, let's see. Can you go up and make a function?
Yeah. Yeah, here it is. I just simply use the same one which Science shared in that Excel, that statistical learning.
What is the sample size over here in this data, which I have not seen actually? I'm sorry, I have not seen the data.
1,300 something.
1,300. Can you plot the Q2 plot? I'll give you the code right away.
Okay.
Let's see, because the data should be normal. I'll give you the simple probability plot. Can you try to run this?
I'm not able to see the chat screen.
You have to go down and you have
Yeah.
more. Yeah. The data
This
you
one?
have to input it. So input data you just make DF of DF6. Or like, yeah, BMI mail, yes. You can make BMI. Directly input the BMI mail over, it will take it.
Yeah.
It's normal.
Yeah.
right? You get
But
this
when
straight line probability plot also.
yeah,
So in what test you have used it? Check
Shap-
normal
not
distribution. Use
yeah,
Shapiro test, right?
no normal test, normality test K2.
Shapiro test also have you tried?
Yeah, yeah. Shapiro also it shows the. One second. See, that is also values coming like this, less than 0.05 only.
Okay.
Probability not Gaussian.
Okay. Okay, Sunil, let me also check it. I'll check it also.
Okay.
Maybe today and tomorrow, maybe something.
So
Then
that's the purpose of that Shapiro test, right? So statistically prove whether the data is normal or not. Right? The way I'm using that is right, right?
yes, yes, yes. You're using right only. And at the actually you should get a zero value. If 1,000 number
Yeah.
of points are there, and it's
Hence,
probably
I have one question over here. Like the way which we use for different tests, we have different inputs. One you have to use a categorical, other you have to use a numerical. But Shapiro, in which category we are going to use it, I'm not sure on it.
yes,
Because if you
yes.
take chi-square, it has to go for categorical. And whatever the test you are trying to unravel, male and female is kind of another test that, because you are going for numerical and the categorical.
No, but if you see the data for data which he is having it, can you put the data directly BMI? Can you just put
Because he's separating
that is
male and female using
numerical
BMIs, I
data
guess.
only.
Yeah.
That is numerical data only, right? So
Yeah.
Yeah.
that is numerical data only. At the end, this is the data of numerical order.
Numerical, and you are using the categorical also. BMI is your numerical, but you are using the male and female as a categorical over there.
So this chi-square is for significance, no, but he's not doing the significance test, right? He's doing the normality test. Venkat, he's not doing the significant test right now. If he's doing the significant test, then what you're saying is right. But he's checking that whether that particular data is normal or not normal. You're getting this?
Yes. Yeah, I'm getting it.
So there should not be any there should not be any, even if the sample is basically normal, you should get the normal, right, directly. The p-value should be you should get the Shapiro as a probably Gaussian only. So because the data he's talking about the category is a normal continuous data.
Numeric, yeah.
Significant test he is not doing it right now. And anyhow, this is not counts, right? Again, chi-square test is only for counts, Venkat. That is when you're
Yes, yes, got it.
yeah, when you have a contingency table, and that this is again a t sample. Maybe he'll use a t test only, two sample t test. It will not be a chi-square test over here, even if it's male or female. Because if you remember, uh,
It's not
categorical.
a chi-square, it's ANOVA.
No, categorical to numerical, you had this t test and ANOVA test only. Categorical to categorical, you have a chi-square test.
Yes, yes.
Correct. So and here anyhow the categorical to numerical is there. No, he'll use t test only. Chi-square test will not come into play over here.
So what are the test
Can you
method you
pass whole
applied,
column?
Sunil?
Yeah,
Sunil,
I
can you
used
just
two sample test. I mean independent test.
Correct,
that's
correct.
correct.
That is logical only.
But my only doubt is like visually it is normalized, but on using the techniques it is not showing. That's what my confusion is. Whether I'm doing right or
I'll also check, and other people also can check it because other experts also there. I'll also check it, Sunil. Let me
yeah.
still give it time till tomorrow because I'll start the assignment today maybe. Then I'll see tomorrow.
Okay. Yeah.
Right.
And
Now I'm
I
getting out. Visually, we should not go, right? We should go as per whatever result. P-value low, based on that only. Visually, my understanding, I may be wrong. We should not go with visual. Visual may look like a normal distribution, but we should go purely with p-values.
Sendil, that is when you are doing the statistical analysis. Like I made a for loop, right, for extracting the features. That is for that kind of thing. When I saw you saw, right, I made a for loop extracting the features. When you want to write a code for multiple number of variables, you can use a statistical test. But at the end, when you are using a normal single 4 or 5 variables are there, it's easy to do the visualization and select the variable. For suppose 6 7 variables are there, you want to select it manually. You can do the EDA and you can do it. It's basically actually it's nothing but EDA. This is nothing but EDA of it. So what you're saying is right. When number of variables are quite high, then you'll run a for loop, like I also showed, right? Then you'll extract the significant features. Then you can do it. Otherwise, you can directly use the for 4 or 5 variables. I guess maybe as per my knowledge, I don't know. Maybe other expert also there. So other people also there who are actually into these things day in day out. So they can put a comment on this. But this is as per my knowledge. I don't know. Other people can want to comment on this. Selva, Venkat.
What was the question? Sorry.
No, Sendil had a question that you don't have to see the normally. At the end, you have to do a statistic test only to know whether something is normal or not normal. So what I was saying is we have 2-3 variables only. Then you don't have to set the p-value of each individual things for normality. Yes, you can do the ED directly like this probability plot or histogram. Based on you can see whether it's histogram like normal or not normal. When you have number of variables are very high,
Even here also, Vishal, if you look into the plotted line, the theoretical red line, and on top of which where our data is plotted,
correct.
Theoretical line. So here it is not just overlapping. If it is matching point to point, then it can be a normal distribution. Normality is there. But in this here, if you see at the bottom and the top right, there are some deviation. Maybe we need to check. I'm just telling my thoughts. We need to check on it. It is like point to point matching on the theoretical line. It is normal distributed.
Based on my experience, always this is very good actually match. As per my knowledge, this is very good match. And any practical data set, even if you not get this much normality in any practical data set, this is very highly normal.
Yeah.
If you see,
that's the reason.
Probability.
When we actually, go ahead, Vishal.
No, please go ahead, Sandil. Please go ahead.
Yeah. So that's the reason. Generally, in my organization, I work for Ford. They will say, don't go with the distribution by looking at whether it is bell-shaped curve. Look at the p-value, and based on the p-value, you need to. Sometimes it may even be like we may miss a lot of production data will look like normal distributed. You have a bell curve.
Okay.
With that, I used to previously say that that is normally distributed. That later my quality the team head I used to say, no, don't look at the drawing and say it is. Look at the p-value. Now you tell. So that's the reason I'm sharing.
Okay. Maybe there's a I don't know. Sandal, thanks for sharing, because I'm not the industry expert in this one. Maybe other people can comment on that.
Sure. I will also do same thing. I will verify and I'll update.
Yeah.
Sunil, actually, what you need to do, you need to apply t-test, independent t-test. Okay, separate out male and female. You can pass those data set, the filter data set into t-test. You will get the p-value. Now you have done for male data set you identify a p-value, and female data set you identify the p-value. You remember in class, right? One of the I think FEMA data set, FEMA or cancer data set, we apply the same. You remember that?
Yeah.
His
Okay.
question, his question, even he was putting BMI male and BMI male, they are individually also normal distributed, no? Even if it's like only BMI male or BMI female, they seems like normal distributed. Even in the QQ plot also they are getting normal distributed. Then why not just Shapiro test? Why not in Shapiro test? It should be coming in the Shapiro test also. That is his question. Individually also, if he's getting it in the normal plot or by the visualization also, he should be getting there also. Sunil, can you try one more?
Shapiro test is opposite, right? If there is p-value is high, in this case your normalization, your distribution is normal. Okay, if p value is less, it's abnormal.
Correct. So he's getting very less p value, no?
Yeah.
Can you try, Sunil, the unique value of
No,
B?
no, no. Here, no. Here, the problem here is he identified the p value for only male. See, can you please try with this? No, let me ping you.
Okay.
Uh,
You want to append and try?
see, can you please try this? Your
One second.
X is a male data set, Y is a female data set. Can you
Say
please?
it. This is not t-test. He is not trying t-test. He is not facing an issue with the t-test.
Yeah.
Facing
In
issue with
t-test,
zero test.
t-test, it is fine actually.
Can you try, Sunil, the unique value of it? BMI male, how many unique values are
Okay.
there? Out of total value, what is the unique values? Because Shapiro test gets a bit wrong value when the number of unique values are less. Unique
676.
out of
1300
1,000. There are
plus.
multiple values.
But
How
I
many?
tried that the other test as well, right? Normality test that doesn't that is specially for this kind of scenarios, right?
Okay,
That also showing that
same error. So
yeah,
we'll
same
have,
kind of
Vishal,
value.
like
okay.
Shapiro test is used for the like continuous variable, right?
Correct.
So maybe here it is like male, female. We are it's
No,
kind
no,
of a categorical count.
no. Again, BMI is, if you go, Sunil, he has shown also, right? The data isn't
Yeah,
normal.
BMI is a continuous variable.
It's a
Yeah.
continuous only. No? BMI is continuous in nature.
Okay.
So what are the tests you applied,
Okay.
Sunil? Shapiro test.
As well as normality test both. I can show you.
Sunil, again, it's we have to see it. It's quite surprising also for me also. Maybe everyone can see this.
Yeah.
We can try this thing by ourselves also. Maybe we'll come to,
Yeah.
we can discuss on the chat or maybe Google Classroom, and if someone find a solution, we can put on the Google Classroom.
Yeah.
People who has not joined local classroom, please join also. Who has not joined, because we keep on sharing the things and it will be always, it will be there. You can always refer in WhatsApp and chats and all. What is happening? So many chats are happening. It's being lost. That's why I keep
Yeah.
Google Classroom. People can go and check it over there. So Sunil, we can discuss. Sunil,
Okay.
I also found this. This should not be happening. Let's see. Everyone can see this, and everyone can try. Then we can come back together. We'll see.
Okay. Sure.
Okay.
How many tests to be applied? Yeah, all the tests or any one or two are fine.
What does that say?
So how many tests to be applied in the assignment? Hello, can you hear
I'm
me?
not, yeah, I tried only one, but just you mean the normal distribution you're talking about, or the
The question number 4.
uh,
Question number 4. Let me take the PDF.
no?
Question
I
number
tried
4 will
only
have
one test.
one test.
Yeah.